And those extreme conditions involve very tiny length scales and very high energies, which, when did that happen? When do we naturally have that happening? In the Big Bang, right? So maybe that is a good point at which those could be studied for, in some way, if we could, you know, study that or probe that, even if it's only theoretical, or if we can get some clue from the cosmic microwave background radiation, which is from, you know, the early universe, not the Big Bang, but it is from when the universe was only 300,000 years old, which is much, much younger than what it is now. So if we can understand anything at all about the Big Bang or soon after, where soon is of course relative, because, you know, hundreds of thousands of years is still, sounds like a long time to us, but it's not a long time with regard to the universe. So this is why people might obsess over the early universe quite a bit in cosmology and look to cosmology to give us some of these answers about the nature of gravitation and this theory of everything candidate that can explain both gravitation as well as quantum mechanics, including, of course, the three non-gravitational forces like quantum electrodynamics, taking into account, of course, electromagnetic force, strong nuclear force, weak nuclear force. We already kind of know, and we actually looked at that it needed supersymmetry somewhere in the picture, but basically the three non-gravitational forces can be unified if you consider very extreme scales of energy and length. Length being very tiny and energy being very high, or very high temperature. So those types of conditions are difficult to reproduce in our current state in the world and in this current universe. But one can imagine that being exactly the similar kind of thing when the universe was getting started in the Big Bang. And so thank you so much for your support. So that is really where it's not just cool to talk about the Big Bang, and it's not just, you know, cool to understand the early universe. It might be the only sort of experimental test bed for us if we can probe it, even if that means that we probe moments after the Big Bang and not quite as far back as the Big Bang. It might just give us the only way to probe such extreme conditions and get these answers out that require those extreme conditions. So we keep mentioning, for example, that superstring theory, we only call it a grand unification theory or a theory of everything candidate because it cannot be tested. It cannot be tested with all its extra dimensions. Some of those extra dimensions are very tiny, so tiny that they cannot be tested, right? This is the issue. We would be, you know, there comes a point where there's enough desperation for a theory of everything where we are willing to accept some crazy theory with a lot of dimensions if it can be tested. But if it cannot be tested, then we're stuck with a candidate versus a real theory. So even that sort of issue, right, the testability of superstring theory, again, might be possible if you can probe back to the Big Bang and moments after the Big Bang.